Ah, there we go. Okay, so these are just the syllabus. You probably already have it, but we'll go through it again. Hey! What's? Come on. Yeah. Over this way. Well, that was. Where was I? Over here? Yeah. I'm gonna go all the way around. Come on. I don't have enough. Pass whatever you got over there. I thought I ran off enough. There's an extra. Okay, and by the way, there are just microphones on your tables. So when we get to class participation, you'll be able to participate, and it will listen to what you're saying. So okay, so I'm Mike Jacobson. My office is down the hall here. The class time. Okay. As I said, we'll be videotaping every class almost, and I'll talk a little bit about that in a second. That's my YouTube channel. That's the YouTube channel for this class, 4408, 5408. I have other channels for other classes. My office hours. Will those work? 2 to 4 on Wednesdays? Yeah, class is Tuesday to Thursday, right? Tuesday and Thursday. Okay, so Wednesday 2 to 4, Thursday 12 to 2. We're in this room. Most of you seem to know Canvas, the book. I don't see too many books. So have you been able to find the e-text? This is the book. Okay, there is an e-text. You can't get it from World Scientific, but it is available. It's around somewhere. Assignments, if you went through this, let's see. There's going to be some homework assignments. 5, 6, 7. Depends on how ambitious I am. The total percentage for the homework assignments will be 20%. If there are 7 of them, you can figure out that it's 20 over 7 for each one. If there's 6, it's higher. The 2 midterm exams will count for 50%. Final will be 30%, and the final will be on final day, whenever that is. Probably Tuesday of finals week, I'm going to guess. But don't hold me to that. 90, 80, 70, 60, those are the grades. Canvas, you can always check your grades. And then there's course procedures. Don't be absent on exam day. Drops and incompletes. You can read through this. And I know this is the hard one. So I would ask you to put your cell phones away, but I know that your book sometimes is on your cell phone. Don't be texting. Okay. Don't show me a little respect. Just a little. Not too much. Okay. Questions? Okay, here we go. So, first of all, if you're thinking graphs like this, you're in the wrong place. Okay, we will essentially never look at graphs like this. Right? We're going to be looking at completely different objects, which we call graphs. So, if you started reading the book, and if you've read anything about graph theory, rumor has it that graph theory started with in the mid-1700s with the bridges of Königsberg. Oh, they're going to have to do better cleaning these boards. and I don't even really know where Königsberg is. Sometimes it's in Hungary, sometimes it's in Yugoslavia. It's somewhere in Europe. And the Pregel River went through Königsberg. And the Pregel River had 2 islands in it. And there were bridges. There were bridges, 2 bridges. Two bridges from this island to each side of the river, a bridge across the islands, a bridge from this piece, and a bridge from here. So those correspond to bridges. And, the story goes that the villagers, the bridges in Europe are magnificent. There's no doubt about that. And the villagers in Königsberg wanted to traverse these bridges and cross over each bridge exactly once and end up where they started. Okay, so let's see. Traverse each bridge exactly once, end where you started. Okay, take a minute. Draw down the bridges of Königsberg, and can you do it? Does everybody understands the question? Okay. It might be easier on your paper to go like this. Anybody, can you do it? Does everybody understand the question? Cross each bridge, beautiful bridge, each one, exactly once. Start, anywhere you start. Let's label this A, and this piece B, and this piece C, and this piece D. So you can start at any one of A, B, C, or D, and you traverse each edge exactly once, because each bridge has its own beauty. You traverse each edge exactly once and end up exactly where you started. So you're going to cross 7 bridges. Anybody? So this was sort of what is considered as the start of graph theory, and you're looking and you're going, huh? The story has it that this was sent to the famous mathematician Leonhard Euler. Euler, have we heard of Euler? Maybe he's good for something. So in the mid 1700s, this problem was sent to Euler. And from this problem sprouted a whole field of mathematics called graph theory. Okay, so now we want to give some basic ideas of graph theory. So what Euler decided to do was, well, it doesn't matter whether it's pieces of land or let's use that dot. That's A. And here's B. Here's C. Doesn't matter where we draw it. Here's D. And there's two connections between A and B, and two connections between, and let's see, there's one from A to D, from one bridge here, and one bridge here. And in the literature, essentially this is the first appearance of what now is called a graph. This is the first real graph that appeared anywhere in the literature. And we'll come back and make that a whole lot more specific, and actually we'll decide the answer to this problem. Remember, there is a problem related to this, and all we've done so far is made this thing. Okay, so let's actually define a few things. So when I started learning about graph theory, it wasn't so sophisticated. It wasn't in the 1730s. I'm not that old, but it used to be called dots and lines. But it's grown up a little bit. So we have dots, which we're going to call points, or vertices when we're really grown up. And we will stick primarily to vertices. And then we have these lines, which are called edges. So I'm ready to define a graph. A graph is a set of vertices with some, and I'll underline some, put quotes around it, because we'll see how that relates here, with some edges, which are two-element subsets of vertices. Okay? So that's the transformation from land masses of Königsberg and bridges to the idea of graphs and edges. Okay, so let's before we actually prove this. So I have vertices and edges. So and let me point out that we're really going to define a multigraph. When I get to defining a graph, we don't like these multiple edges. We don't like that there are two edges between A and B. There may be some applications, case in point, where having two edges between two vertices becomes something of importance. So we may want to actually have that, but a multigraph is a set of vertices and a multi-set of pairs or two-element subsets. Okay, and that's it. You're done. That's graph theory. Okay, so just if you.
What's the difference between a set and a multi-set?
Okay, so a multi-set. So okay, so let's look at this. So I have a pair AB, but now I have another pair AB. So the pair AB would be in the multi-set twice.
Oh, so it's just a set
It's-
where the elements are allowed to be
They're
repeated?
allowed to be multiple times.
Oh, okay.
Right.
Thanks.
Okay. In fact, most of the graph theory that we'll look at, we will not be looking at multi-sets. Okay, so the book gives you several interesting examples. Okay, so I want you at your tables. Okay, by the way, page 1, there's the bridges of Königsberg. Okay, so, on page 2, so the bridges became this. Notice I'm not giving you the answer yet. That's for you to figure out tonight. And then there are examples. So here's an example where a graph represents, the vertices of the graph represent land masses, and the edges correspond to bridges between the land masses. So that's one representation. So at your tables, I'd like you to look. Is there a book at every table? I hope. So there's the lovely thing about this book is there's lots of examples, and I'm going to mention that there are exercises embedded in each of the chapters. There's exercises, and we'll do some of the exercises. And then, lovely, at the end of every chapter, there's something called a problem set. So most of the time, I will assign. You should do exercises. The exercises in section 7.4 and 7.5, and then for homework to be turned in, there are problems from the problem sets from chapter 6 and 7. Okay, so we will distinguish between exercises, which are simple exercises, versus problems that may give you problems. Okay, they're maybe a little tougher. Okay, is that clear? You're going to stop me and ask me questions, but you'll catch on. Okay, so at your table, I want you to look at example 121 through 125. And so 121 through 125 give you 121, 123, 122, 123, and 125 give you examples of how graphs might arise. 124 asks you to come up with an example of how a graph might arise. In fact, it asks you to come up with 3 examples of how a graph might arise. Okay? Go. And watch out, there are microphones around, so be careful what you say. You have no book? Anybody else? If you don't have a book, go to a table that has a book. Sorry. They're pretty light. It's pretty small.
Yeah. I think it's just like showing us why we might translate it into a graph. Yeah. We can draw it out if we want to.
Do you have an e-text? You are buying one. Okay. You may not like the class. No, I'm kidding. You all have a book here? You have an e-book? Yeah. Did you get them? Okay, okay, good. I don't hear much chatter.
What's that? You're looking for a copy of it?
I can find one actually. There's a place that has just a lot of text.
Oh, nice. Let me know if you find it.
I will. I actually I have a copy of it that I already found.
Oh, you do?
Just not on my phone.
Okay, gotcha.
Do you need one or something?
Yeah, can you email it to me?
Sure.
So let's see. How do you do it? Okay, so V only. Only question. Right hand, the letter train with the one. And then we'll put the zero. Okay.
We should
I'm
do
gonna do it.
You work a lot.
I do. Okay, so we have number text. Oh, yeah.
Thanks.
Yeah.
Yeah, so
Thank you very much.
Yeah, I can actually just give you the website if you want.
Oh, okay. Sure.
I'm just not really sure, ethically speaking, how okay the website is.
Oh,
but,
sure.
But that's why I feel a bit bad about it. But if you're interested, I can actually post a link to it.
Okay, cool. Yeah, that'd be great. Thank you. Okay, so what are 3 examples from our everyday life for which graphs can be applied? How about adoption? Kids that need to be adopted, and parents that may or may not want to adopt kids. Okay, but they're prejudiced, right? You know, this family only wants kids that's that's younger than 7. Okay. Okay, and you know, I don't know. Anything else you want? There you go. That's graph.
One thing that's moving, so we got one thing.
I think we're kind of, I guess like almost like traffic flow.
Okay.
So we have, you know, these intersections. And let's say here to here, you can do that one, but then here is like one way, or between these two is under construction, so you can't do that.
Are we allowed to have arrows and things saying one way and stuff?
I would think so.
'Cause I think we just have, right? Because I think we just have vertices and edges, 2 element subsets.
Kenny, are you allowed to take pictures and stuff?
No.
Okay, so you've had, I know, not much time to look at this, but does anybody want to share an application, an idea that they had for what, how they might model something using graphs? Okay, so your vertices would correspond to atoms and bonds, and then you would connect an atom with a bond if they could have that that bond together. Okay, good. Yeah.
I don't know if this is true, but I've heard that neuroscientists look at neural networks in the human brain using graph theory.
Of course, I mean, you know, there are nodes in your brain that they don't talk to all of them. Okay, so they only communicate with, and I gave half of the problem away. They only communicate with some of the other nodes in your brain, and that forms a graph. So in fact, a network, any network, phone network. Do they still have phone networks? Maybe not. Electrical, heating, anything that goes to different places. That forms a graph. Anything else? Do what? Family trees. That's a graph. Everybody knows what family tree is, right?
Asking about the mail system, so do they need to use the graph theory to try to figure out the least time to deliver thing to the customer?
Of course. So delivery system. So you have so many delivery points. You have Amazon is delivering with those things, and they have given the demand on each of these centers, we need a edge between a center and the house that ordered this. Oh, come on, okay. Constellations is a graph. The Big Dipper is a graph. Okay, and only kind of some edges between the points. So let me give you one. So courses and professors. So we have a list of courses that have to be offered. And professors like me only want to teach at 2 o'clock. So there's only so many courses I can teach. So I'm a node, and I teach one of the 2 courses that are offered at 2 o'clock. And that's my teaching load. It's nice how that works. That was funny. Maybe not. Okay. So there's lots of applications, and we'll be seeing lots of them. This is not an applied problem. This is not an applied course, but you should let your whenever you see a picture of the brain. Whenever you see a picture of the brain, you might think, oh, that's a graph. And there are many. There are ways of pairing medical students up with medical schools. Forms a graph. No? Oh, I thought someone was commenting on that. Okay, so now let's get down to business. Okay, so a graph. Let's get formal about this. So I have a multi-graph. So I have a set of vertices. So typically, I might slip and call it a point. But typically I will try very hard to call it a vertex. Vertex is one. Vertices are many. And vertice doesn't exist. Okay? So V is a vertex. V and W are vertices. Not vertexes. It's like nails on a chalkboard, and so we'll have a multigraph has a set of vertices. So we'll call our multigraph G. I mean, you don't have to call it G. It could be M. It could be H. It could be your favorite letter. I'll just call it V. So we have V of G is the set of vertices. And then we have pairs of vertices, which we call edges. This is the set of edges. And you've all seen some now examples of vertices and edges and graphs that are presented that were presented in these examples. A lot of this is terminology, and I do apologize for this, but once we get past the hurdle of terminology, then we'll be able to do some neat stuff. So, the number of vertices, right? This is cardinality like you learned in Math 3000. So the number of vertices, the size of the vertex set is called the order of G, the order of G, and the number of edges is called the size of G. Okay. All right. Let's see. So we want to bring in some of the things that you've done in previous classes. We're not going to do any theory at this moment. But, sometimes having a graph so let's imagine that's my graph. It's not so easy to actually demonstrate the graph. Sometimes they have many more than 7 vertices. So we represent this sometimes with different mathematical structures. So we have what's called the adjacency matrix. Okay, so if there's an edge between U and V, there's an edge between U and V, we say that U and V are adjacent. Adjacent. So if U, V, and now I'll use some notation. If U, V is in the edge set, then we say that U and V are adjacent. So we're going to develop your favorite thing, a matrix. Okay, let's imagine that my vertex set has n elements in it. Then my adjacency matrix, A, is an n by n matrix, where Aij is equal to the number of edges between I and j, vertex I and vertex j. Is that clear? So, for example, let's see, we would have a 4x4 matrix. 4x4 matrix. There's no edge from A to A, no edge from B to B, no edge from C to C, B to D. So the number of edges between A and B, so if we look at this as A, B, C, and D, A, B, C, and D, this is a 4x4 matrix that I'm trying to draw. The number of edges between A and B is 2, so we'll put 2 here. The number of edges between A and D is 1, and the number of edges between A and C is 0. By the way, at this point, the number of edges from each of these points to A is the same thing. So there's a symmetry. This is a symmetric matrix. So the number of edges from B to A is also 2. Number of edges from C to A is also 0. Number of edges is 1. And let's see, what am I left with? C and B is 2 and 2. And D and C is 1 and 1 and 0 and 0. So there's the adjacency matrix for the graph of the bridges of Königsberg. Now, at some point later on in the semester, we may do something with the adjacency matrix. Okay? At this point, it's just a thing. It's just a way to represent. You decide: is it nicer to have this or have this? Let's see. So let me draw this as a graph and not as land masses. So here I have 4 vertices. Okay, so there is a graph, and this graph is represented with this adjacency matrix. Okay, it helps if you actually label this, then it makes sense. Okay, questions? Again, one of the things about if you leaf through the first chapter, there are many. I can't stress enough. There are many graphs. None of them are necessarily important. They're just for you to play with at this point. Playing is good on day 1 of graph theory. Okay. Okay. It's at so I have. Let's see. I've done the Okay, so the set of vertices, I've got the order, I've got the size of the graph, that's the number of edges, and multiple edges count multiple times. It's adjacency matrix, incidence matrix. Okay, so what else would you like to know about a graph? What other sort of things pop out at you as being important? Do what? When you have a one-to-one thing, you're looking at a mapping from. So, are you looking at a one-to-one mapping from the vertex set to the edge side? I mean, that we'll talk about. Those are special. We'll get to something like that. But what else might you like to know about graphs?
How about if there's if you have given an order or a size, is there a limit on the other one?
So when you say, so if I say a graph of size 5,
Yeah.
so that has 5 edges.
Yeah.
Okay. So I'm also going to I didn't mention this. Okay, so here's a graph. So we could have edges that it's a pair, and the pair could be repeated. And he makes a big he sort of indicates this is called a loop, right? When the two endpoints of an edge are the same endpoint, it's called a loop. And at that point he says, yeah, we're not going to deal with loops. Okay, so he'll throw those out. Okay, so if I throw those out, then it's a matter of how does the relationship between number of vertices and the number of edges, and we'll look at different relationships between two. Again, loop, you should know that they're there. He defines it. If you turn to page, which you all don't have your book, but if you turn to page, he mentions it early. Maybe on page. You see a loop? Oh, there it is. There on page 5. There's a loop. If you look at example 1.2.5, there's a loop at vertex V. So the edge is VV. It's not very interesting. In some applications, it's important. I mean, that may be something that is important in an application. Whether you're looking at blood vessels in your body, there may be blood vessels that start at some point and come back to the same point and hit nothing else. It would not be probably good for you, but it certainly exists. Okay, so again, I can't encourage you enough to be drawing graphs. And just for the sake of looking at them mathematically, you may want to look at their adjacency matrix. Okay, and there's lots of graphs given in chapter 1. Okay, so back to so. Okay, so I'm going to draw. Let me draw a graph. This is not an important graph. I'm just drawing it just for the heck of it. Let's go like that. Okay. Okay. So what have I've already defined? I know that the order of this graph is looks like 9. Right. Order corresponds to number of points. The size. Count them. Let's see. 4, 6, 8, 10, 11, 14, 15, 16. Is that close? Something like that. Okay, so we can count the number of edges, we can count the number of vertices. So we know the order and the size. The way you draw it, it doesn't, at this point, no. Unless it's an application, unless this is representative of some system in your body or transportation network or road system or synapses in your brain, it doesn't matter how you draw them. Their physical location, it doesn't matter. Let me show you my favorite one is, here's a very simple graph. And here's the same graph. Okay? Does everybody see that that's the same graph? Okay? 4 vertices, 4 edges. In fact, if I look at this and this, and this and this, then we can order in the same. Let's see, we call this A, B, C, D. And then we have A, and A is adjacent to B and D. So I guess that's C. It's the same graph. Okay? And by the same graph, I mean the vertices are the same and the pairs of vertices or edges are the same. Okay? All right, so incidence matrix. Okay, so I'd like to look at a graph, and I would like to and imagine these graphs could be a million vertices. I mean, in a real application, if you're looking at the airlines in just the United States, and all of the airports correspond to a vertex in your transportation graph, and we're going to connect two airports if there's a direct flight from Denver to Kansas City. That's 2 of the points in my graph. So we can imagine these could be pretty large. So what I would like to do is sort of get some idea of the scale of these graphs, and again, they could be very large. I pick a point V. I haven't done this right. The degree of V, we haven't talked about that. The degree of V, which I am going to have to really work on. The book abbreviates that as D of V. If I sort of lose my mind for a moment and refer to it as DEG of V, you'll understand. To me, it makes more sense as DEG, but the book uses D of V. The degree of V is the number of edges incident to V. So that's the degree of a vertex. Then I know the order of the graph. I've talked about that. The order of the graph is the number of vertices. The size of the graph is the number of edges. The degree is of a vertex is the number of edges at the vertex V. And when we're going to get to a point where we're talking about many different vertices and possibly many different graphs, we might want to specify that we're looking at the degree of V in G, if the graph is G. So let's say this graph is G, and G is part of a much bigger graph. This is G, but it's part of a much bigger graph, H, that looks like this. I should have drawn this in a different color. Okay, but here's H, but here was G. Okay, so we're going to be looking at subgraphs of a bigger graph. So we're going to want to know how many vertices there are in the subgraph, how many vertices there are in the big graph, how many edges there are in the big graph, how many edges there are in the subgraph, and what's the relationship. We're going to see that there are relationships between the two. Okay. Now, one of the nice things, I'm a graph theorist, so I study a lot of the structure of graphs. And one of the things that someone once told me about graphs was that the terminology all made sense. I never really necessarily agreed with that, but let's suppose I have a vertex X. If you had to guess, what would you imagine the neighborhood of X would be?
Everything connected to X with a distance of 1.
With a distance of 1. The neighborhood is precisely the vertices, the set of vertices. Let's make sure. Yep, so that's the neighborhood. Is the set of y in the vertex set such that x, y is an edge. So that's the neighborhood of x, and you know we need a notation for that. So I'm going to move this over a little bit. Y in V. So it's the set of y's in the vertex set so that xy is an edge. Okay, everybody, that notation is okay. And again, you're going to spend the next 48 hours just cramming, just drawing graphs. You're going to be dreaming about them. Maybe. Okay, so this is the vertices that are adjacent to it. What do I call the people that are close to me? I know closeness. In reality, what do we? Neighbors. Oh, this is the neighborhood. This is the neighborhood, and we abbreviate this as the neighborhood of X. Sorry, the neighborhood of, neighborhood of X, n of X. By the way, the order of the neighborhood of X is equal to the degree of X. So we use a lot of mathematics notation that we've learned along the way. So the cardinality, this is a subset. This is a subset of the vertex set. And then the number of elements in this subset relates to the degree of X. Okay? Nothing, there's nothing at this point that jumps out at you as being hard. We haven't proved anything yet. It's coming. Okay, so I got neighbors, I got neighborhood. I'm going to change this graph and add a vertex. So I went from this graph ABCD, and now I have this graph ABCDE. If you had to guess and give sort of a name for E, what would you say? Empty. Well, its neighborhood is empty. But in terms of this graph, what can you tell me about E? A lot of the terminology makes sense as we would say it. E is isolated. So E is an isolated vertex. So any vertex of degree 0 in a graph, any vertex of degree 0 in a graph is called an isolated vertex. Sometimes an isolate. Okay. The last thing I want to talk about before we actually prove something. Yep, we're going to prove something. So we have vertices of degree 0. Vertices of degree 0 what? What was that?
Isolated.
Isolated. So vertex of degree 1 is called an end vertex. Okay. So those are two more special graphs. Okay. So here is theorem 1. I'm going to erase all. Any questions? Anytime you want to ask a question, you either blurt it out or you raise your hand.
For the matrix,
Huh?
D and B and D, would that be 1?
Sorry.
No, BD.
So BD.
Would that be 1?
Oh, shit. Yeah, of course. Sorry. Yes. Yes. Now, what was I saying? Okay, yes, I know. Questions? More questions? If I make a mistake, tell me sooner.
Well, I was trying. So if you add them up.
What?
Times,
What? If you add what?
like those numbers up, you're gonna get the size of G.
You're gonna
Is
get
that right?
That's.
Is that right?
Are you sure? Oh, look what. So say that again.
If you add all the numbers.
All of the numbers.
No,
Wait.
half of it. Like,
Oh, how do you know? Half of it. So, okay, so the diagonal is zeros, and if I add 2 plus 2 plus 1 plus 1 plus 1, we get what?
7.
And how many edges is that?
7.
Ah, okay. So, what if I add up all of them? You just stepped into the proof. What if I add all of these? You get what? Twice what? Twice of the edges. Okay, wait a second. So what am I adding there? So what are we adding up? So one more time. Here's a graph. Usually this is how I draw my graphs. There's a graph, and here's an edge in the graph. So this edge contributes how much to the degree of this vertex? And how much to the degree of this vertex? 1. So if I look at the sum of the degrees, so imagine my vertices are labeled x1, x2, x3 up to xn. So those are my vertices. Sorry, let me not abbreviate at this point. Okay, so if I look at the sum over all the vertices in my graph, and I take this point and I look at the degree. I take the next point, I look at the degree. Not look at it, I add it. The degree plus this degree plus this degree plus this degree plus this degree. Just like here, this degree plus this degree plus this degree plus this degree, or I've erased it as a graph. This degree plus this plus the degree of A plus B plus C plus D. How many? Each edge is counted twice. Each edge count. So wait a second. The sum of the degrees. We just did our first proof. Oh, proofs in graph theory are going to be easy. Yeah. Okay, so now your homework is to actually write down a proof. The proof in the book is there's a proof in the book, so you can look at that. But we just proved that the sum of the degrees of any graph is twice the number of edges. And again, the proof is that if I look at an edge, it contributes twice. It contributes to the vertex of each of the two end vertices. Okay, so it contributes twice. So you can do this by induction. I remove an edge, assume that it's true, so the degree of the vertices with one edge removed is twice the edges minus 2 times e minus 1. Now I throw this edge back in, it adds 1 to this one and this one, so we would add 2, and now we have another proof. Induction. That's a 4-letter word, right? That's a joke. You're all supposed to be laughing at that. Okay. You all liked induction. Induction is used on several occasions during the course of the semester. Okay. So that's theorem 1.3.6. What's 1.3.9? Oh, yeah, of course. So the sum of the degrees is even. If I take any graph, the sum of the degrees is even. Sum of the degrees is even. So how many vertices? What can you tell me about the number of vertices of odd degree. What? The sum of the degrees of all the vertices is even. How many vertices of odd degree can we have? What can you tell me about the number of vertices of odd degree?
Well, I mean, if you have 2 points.
3,000, math 3,000. Raise your hand if you want to admit that you've had math 3,000. Come on. You know, and enjoyed it. Oh, there you go. Okay, you can put your hands down.
Vertexes that have an
Okay, wait a second. Let's. What am I? What can you tell me about the number of vertices of odd degree? So I've got. Let's say I take the vertices, and some of them are even, and some of them are odd. Even plus even plus even plus even plus even. Add those up, and what do you get? An even number. Now but that's not all the vertices yet. Now I got odd and odd and odd and odd and odd and odd. Odd. Can I have 5 odds? Okay, let me back up. Can I have 5 evens? Sure. Can you draw me a graph that has 5 vertices of even degree? I think so. I can. Maybe you should try. It's not hard. 5 vertices of even degree. It just has 5 vertices of even degree. Yes? No? Can you give me an example? It's not that hard. It's not that hard. It's not that hard. Let me make it easy. Okay. Oh, there's one. Okay, that's kind of cheating. All right, so here's one. 5 vertices of even degree. Okay, 5 vertices of odd degree. That's the whole graph. 5 vertices, odd degree.
Yes. No.
It's either yes or no.
No.
No. Well, why not? Why not? If I have 5 vertices of odd degree, we're saying 5 vertices, then the sum of the degrees would be. Who said that? No, 5 vertices of odd degree. Odd plus odd plus odd plus odd plus. Let's 2k1 plus 1, 2k2 plus 1, 2k3 plus 1, 2k4 plus 1, 2k5. Man, don't run out of steam. Okay. Right? So 5 vertices of odd degree. I don't care what k's. The k's could be a million, whatever you want. But they're odd. There's odd, 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 odd. 5 vertices, that's the whole graph. What do we know about the sum of the degrees of the whole graph? Must be what? Even. The sum of the degrees of the whole graph. Okay, what's the sum of the degrees of this whole graph? 2k1 plus k2 plus k3 plus 3 plus k4 plus k5 plus 5 is what? Is odd. Can you have 5 vertices of odd degree? Can that be the whole graph? Okay, can you have a graph that has an odd number of odd vertices? When I say odd vertices, that means odd degree. Not that they're shaped odd. You're all looking at me like, oh my gosh, what is he talking about?
Can you say that again?
Okay, can you have, and I'll stick with 5, can you have 5 vertices of odd degree? That's the whole graph.
No.
Can you have an odd number of vertices of odd degree? Even if that's not the whole graph. Okay, so let's say I have an odd number of odd degree vertices. Here they are. 2k1 plus 1, 2k2 plus 1, 2k3 plus 1. That's enough. 3 vertices of odd degree, and all the other vertices are even degree. 2J1, 2J2, 2J3, down to 2J T minus 3. I want T points. I have T points. T minus 3 plus 3. What does this tell me? What does this tell me? I sum up the degrees. Start summing them up. Even, forget the ones now. Even. The sum of those are even, plus 1 is odd, plus 1 is. But what do you know about the sum of the degrees of the graph? What was that? Should be even. But so in fact, theorem number 2. Theorem number 1. Theorem number 2. The number of vertices of odd degree must be even. In any graph. So that's theorem number 2. This is Jacobson's theorem number 2. It's book theorem 1.12 or something. Okay, the number of vertices of odd degree must be even. Okay, questions? Look, day 1, we proved something. Okay, so I need a couple more. So now it's just a matter of exploring graphs of different kinds, different types. So if you had a book, okay. So there's I'll draw it. There's the tetrahedron. Okay, there's the tetrahedron. There's the cube. And I don't like to draw it the way it's in the book. I like to draw it because it's a cube. Okay, notice there's a vertex here, and those are edges. I know they're dotted here, but you can't see them because there's stuff covering it up. Okay, there's the cube. So if you go through the regular solids, geometric solids, there's the octahedron graph. If you turn to page 24, you'll see that. There's the octahedron, there's the dodecahedron, there's the icosahedron. They all form very nice, symmetric, pretty graphs. Most of the time, we won't have pretty graphs. Pretty graphs only occur in pretty applications. Most applications aren't pretty. Okay, let's see. So I got graphs, and now you want to be you just want to be drawing. You want to doodle graphs. You want to be thinking about, gee, what if a graph had this and this and this and this, and what can I tell about this graph? You want to be thinking about the structure of graphs. You want to be thinking about different parameters related to the graph. Gee, what's the maximum degree? Oh, by the way, if we look at the degrees, so D1, D2, D3, Dn, those are the degrees of the n vertices. And what can you tell me about the sum of these degrees? This is a graph, and that's the list of degrees. What can you tell me about what can you tell me about? One more time. These are the degrees of vertices of a graph. I'm not drawing it. Just there they are. What can you tell me about? Anything? There's n vertices. And? Anything else?
Either all even or like alternating odd even or something.
Does it have to alternate? All even, certainly that's okay.
They can be odd and even.
They can be odds and evens, but the what? Must the number of vertices be even? Well, let's see. Let's just make sure. Oh, I like to prove things that are not true. Okay, so the number of vertices don't have to always be even. Right? Number of vertices is 5 here. But the number of edges, it's also odd. But the sum of the degrees is even. Okay, so here are the degrees of a graph. The sum of the DIs. I mean, you're not going to be able to say too much, but it's an even number. Always. And as you tonight when you go home and you're just like you're watching TV and you have a pad out and you're twiddling some graphs, you're going to want to make sure that I'm not lying to you. So you're going to want to draw some of your favorite graphs and make sure that the sum of the degrees is always an even number. Okay, and see if you can find other relationships between them. Okay, there's a few more graphs that I want to talk about. And again, this is all from chapter 1. and I draw them in circles, but they don't have to be in circles. So here's endpoints, n vertices. V1, V2, and sometimes I go clockwise, sometimes I go counterclockwise, V3, Vn. That's all the vertices in this graph. By the way, that's also all the edges. So there are no edges. If you had to guess, if you were a graph theorist back in the 20s, what would you call this? Don't be too crazy. Oh, there we go. This is the empty graph. This is the empty graph. Now, I don't like the notation, but he abbreviates this with O sub n. I don't know what the O stands for.
Is that a 0?
Yeah, I don't know. I don't know.
Maybe
It's hard to
a
tell.
0.
Maybe a 0, but okay. So the empty graph has an abbreviation. We don't see the empty graph too often, but it comes up every once in a while. Much more interesting is V1, V2, Vn, and all the edges are there. For every pair, there's exactly one edge, where we're pretty much, we'll see some applications with multi-edges, but at this point, we're just going to worry about one edge between each pair of points. It's up to you. What do you want to name it? It's not up to you, but if it was up to you, what would you name it? Okay, everybody understand I got n vertices, and between every pair of points, every pair of vertices, there is an edge, one edge. What would you like to call it? What was that? For a while, I think someone said the full graph. That's the empty graph, this is the full graph. Yeah, but it didn't stick. Perfect? We're going to save perfect for perfect. I mean, it really has to be perfect. Complete. Okay, so this is called the complete graph. And the graph theorists, the early graph theorists were German, so they abbreviated it KM, and that's how we'll abbreviate it as well. So that is the empty graph on one vertex. It's also the complete graph on one vertex. Not very interesting. Here's the complete graph on 2 vertices. Here's the complete graph on 3 vertices, 4 vertices, 5 vertices. How many edges does the complete graph? How many edges does the complete graph on 5 vertices have? You can count them. I hope. Can't you? 5 vertices. Complete graph on 5 vertices. Well, let's see. We can use some of the things that we proved. What's the degree of every vertex? How many? What's the degree of every vertex?
4. Yeah.
Does everybody see the complete graph on 5 vertices? What's the degree of that top vertex? 4. What's the degree of the next vertex?
4.
And the next one?
4.
Next. So I've got 5 4s.
20.
5 4s. So the sum of the degrees is what?
20.
Sum of the degrees is, what did we prove? Where is it? Sum of the degrees is, did I erase it already? Twice the number of edges. So 20 is twice the number of edges. How many edges are there? 10. Okay? 10 edges. By the way, I will use notation like that's 5 choose 2. The chooses, you did something about that in calculus somewhere. I know, it's been a long time since I took calculus. Okay, so just to, if I look at, and I need an abbreviation for this, so it's Kn, so the number of edges in Kn is n choose 2. And you know the formula for n choose 2. If you took Calc 3, you really did see it at some point. N times n minus 1, let's get rid of that a, n times n minus 1 over 2. Okay, n choose 2. So in particular, K6, the complete graph on 6 vertices has 6 times 5 over 2. See, I bet I could do that. Let me make it clear. I bet you could do that. 6 times 5 over 2.
Is that n times n minus 2?
This is n times n minus 1.
Oh.
Okay, so what is 6 times 5?
30.
Over 2.
15.
Okay. Number of edges in K6 is 15. Number of edges in K7 is 21. 8. I'll leave that to you. All right, let's see. I think I'm almost done with the definitions. One more. Complete, empty, So, graph theorists made up interesting names. Okay, so here's the triangle, better known as the K3. You'll see there are my favorite. One of my favorites is this graph. Has a great name. That's the claw, of course. So we'll see. We're going to see some. You'll get used to naming graphs. Some of your favorite graphs will not have names, and you'll have to make up your own name. But now it's just a matter of practicing these things. So we got complete, we got empty, I got triangle. Okay, I'm out of time. You can just imagine what we mean by a cycle, a path, a tree. Tree, who said tree? Okay, so tree. You can imagine.
Regression.
Huh?
Regression, Joshua French.
No, I'm not him. What time is it? 3:15. Okay. All right. So I'm gonna tell you. Read section 1.2.11.1.2.1.3. It's a lot of definitions. As I said, there's exercises. There's exercises throughout the section, throughout the chapters. There's exercises. Notice exercises for section 1.3. There's 20 of them. Okay. Exercises are easier than if you turn to page. Where is it? If you turn to page 46, there are problem sets. Problem sets give you problems. Okay, so there's exercises throughout the chapter, and then at the end of the chapter, there's something called the problem sets. At this point, you just want to be playing with the exercises. Okay, and I can't encourage you enough, play with them. Play with graphs. get a feel for what the relationship is. There's a lot of definitions that we went through today. And there'll be more tomorrow. Monday, Tuesday, no, wait, Thursday. Thank you. Okay, see you Thursday. I should ask questions? Or are you too afraid to ask a question? No homework yet. Just read and do exercise. Are you in class? Are you in this class? Wow. What happens to you? Wait, let me see. Yeah, okay. As long as, yeah. Do you have to give me a slope or something? Okay, all right. I'll see if I can see it. I'm pretty slow at these things, but I'll see. This has two edges. Okay. It has two vertices and it has two edges. It has a multi-edge, but that multi-edge occurs twice. That's correct. Which one? Correct. No. At this point, this intersection has no edge, and that's what's important. It's only four vertices and their pairs. So I have four vertices, and the pairs are this pair, this one. Here it is, this one. Make up your mind. So are you math major? We won't use, we'll prove stuff. That's a 3,000 is about you've taken another 30 minutes. So they've done proofs in it, right?
I didn't take that.
Yeah.
I don't know how it's
It is a prerequisite. Yeah, I don't know what to tell you. It's things like this are going to come up. Sure, of course. Yeah. If you have trouble, talk to me. Oh, shit. Okay. It's recording.